All right, here's our next challenge. In all this process, we've been dealing with these measurements, essentially both of work when you have expansion or compression of a gas at constant pressure. And when we don't have that, we pretty much just do calorimetry to measure the heat transaction that has happened by the reaction. And then we adjust by the number of moles to get the enthalpy, delta H. We know that if we don't have the actual heat of a reaction, we can't measure it. We can look up the heats of formations of the reactants and products and calculate delta H by using Hess's law. We even saw that for some reactions, what we have is just an ensemble, like an ingredient list of other equations, but we can rearrange them and reassemble them so that we can generate the equation we're interested in. And Hess's law allows us to calculate the final enthalpy of that reaction. But where is this energy coming from? Like, what is exactly the energy that's being transacted to generate these heat exchanges? Remember, heat happens because thermal energy is transferred. Thermal energy is caused by the motions of particles. So when a chemical reaction, for example, is exothermic, what is it doing? Well, it is releasing energy that is causing the molecules in the surroundings, right, in the surrounding environment, to move at faster speeds. In other words, to have more kinetic energy, and that is what is registered as an increase in temperature of the surroundings. But remember, that energy could not have been created. It had to be there somewhere. Yes, we saw before that kinetic energy can be quote unquote stored as potential energy. So let's look back at our model of how a reaction happens and see if we can find out where that energy is at. Okay, so let's consider this. Let's say that during the course of a reaction, what you are doing is, when you deconstruct reactants, what you're saying is you are breaking existing chemical bonds. And when you build products from scratch, you are forming chemical bonds. Now, what do we mean by a chemical bond? Well, for the moment, let's say that a chemical bond simply is a state in which the atoms are brought into close proximity. Right, we talked earlier on about ionic bonds, right? The attraction between positive and negative charges. But we said that without transferring electrons, atoms can actually hook up, join together by sharing electrons, and that brings them into close proximity. Now, when you bring two atoms into close proximity, you have to deal with two forces. You have attraction forces and you have repulsion forces. So obviously, if you have, let's say, an atom that has negatively charged electrons around it and a positively charged nucleus, when it approaches another atom, obviously you could have some repulsion of the electrons of the first one with the electrons on the second one. As we will see later on, the electrons in atoms are dispersed in such a, quote unquote, vast amount of space with respect to the nucleus that they barely get in each other's way. However, the electrons of the first atom could derive an attraction force with the nucleus of the second atom. So that attraction force is going to be important. Now, if you bring the atoms too close to each other, then the nuclei are going to start repelling because they both have net positive charges. Now, what we're going to say is essentially that, in nature, you have two types of, let's say movement or, energy derived or energy related movement. One is you move in favor of an attractive force, like a positive charge moves close to a negative charge. Excuse me, take some water. That is favorable because it's moving in the direction of that force. It's in favor of that force, and therefore that process is giving you a more stable arrangement at the end. The opposite of that is to take two items that would naturally be attracted and move them away from each other. Obviously, the final state is less stable because it went against the tendency of moving towards each other. So essentially, energy has to do with whether a given situation is favorable or not, whether it's stable or unstable. So let me show you the following. I'm going to draw some pictures here and hope I can convey the sense of this here. Let me go back to our camera here. And let's see if I can find this. Okay. Let's talk about the formation of an atomic or a chemical bond. Okay. Let's consider two atoms. I'm going to draw one in black and one in empty in there. And let's say that these two atoms are at a certain distance. I'm going to start them kind of far apart. And I'm going to start moving them closer to each other. In other words, this axis here shows decreasing distance. Okay, when they are far apart, if you consider what's the energy in here, notice that if they're far apart, there basically is, little opportunity for any kind of interaction. But mainly what we're talking about here is for attraction. And we're talking about the electrons of, let's say, that guy and the nucleus of the other particle, and vice versa. What we're trying to do is maximize. I mean, right now you have the electrons, they have an attraction for their own nucleus, but obviously something's holding them away from that nucleus. We'll talk about, quantum models later on. But that's the idea here. So that means that when they're far apart, they are in a situation where you are kind of like away from, or up, kind of like not in favor of this interaction. So the energy is much higher. Okay, so they start here. Now they start moving closer together, right? And you have, more opportunity as they move closer together for this interaction, for attraction forces. So that means that as they move closer to each other, the energy starts going down. Because remember, lower energy means more stability. It means I did not have to keep these guys apart from each other. They are naturally, kind of like falling for each other, so to speak. And they are essentially moving in the favor of the attraction force, which means that you are not having to perform any work to keep them apart. Now, of course, what happens if they get too close? Well, if they get too close to each other, now what's going to happen is you start getting repulsion, because now the nuclei, the positively charged nuclei, are too close to each other. And so now the energy starts increasing because you are moving basically too close and you are generating a force of repulsion. You're trying to move against a natural force of repulsion. You're going to have to put energy into there. Notice that at whatever this distance here is, okay, you have the lowest possible energy. That is the perfect distance for those two atoms to be at. It maximizes their attraction forces, minimizes the repulsions, and this distance here is what we're going to call the bond length. That is the distance between those two atoms when they form a chemical bond. Notice that if I were to form this bond, it's the same as if I had started from them far apart to close together. And that means that you have, this is a higher E, this is a lower E, and that means that delta E here would be negative, right? Final minus initial gives me a negative value. In other words, this process, if all the energy that we're considering here were heat, it would be exothermic. All right? Now, what if I break this bond? Put it over here. Oops. Oh, sorry. Give me a moment. My phone is running out of battery. Ta-da. Okay, there we go again. Sorry about that. So let's say that we're going to be breaking a bond. So now we're going from being close together to being far apart. When they're close together, they have a lower energy. When they're far apart, they have a higher energy, right? Because when they're far apart, you had to pump energy in to move them away from each other, which is where they wanted to be. So essentially, that means that this process, therefore, proceeds with bigger minus smaller, a positive delta E. In other words, we would say this is endothermic. Now, let's consider two different atoms. Let's do another set here. Let's represent these as little boxes. And let's see what their profile will be. Again, we're going to look at the distance between them and what the energy would be. And, you know, it turns out that for this particular example, they start out a little higher. And they have a different profile. Notice that their lowest energy state there is higher. Right? You can see that there's a difference between those two here. And also, the bond length is also different. So not every pair of atoms is going to have the same lowest level of energy, the same energy well here. And also, they're not all going to have the same bond lengths. So in a chemical reaction, I am breaking who knows how many chemical bonds and forming other ones. So essentially, the net reaction is going to be the sum of all of the ones that I form, which are all negative, and all the ones that I break, which are positive. Remember, conservation of energy. Whatever energy I started with, I had to end up with. So if there is a difference between the energies of forming bonds versus the energies of breaking bonds, that difference has to be going somewhere. And that is why you have exothermic reactions and endothermic reactions. So let's go back here to our PowerPoint and start closing it, winding down. All right. So coming back here, we find that, you know, a chemical bond is going to be the position of lowest energy. In other words, it's going to happen when the atoms are at a distance from each other that minimizes the energy, that allows them to take full advantage of the attraction of the electrons of one atom with the nucleus of the other atom. It's like a well of energy, so to speak. So let's look at the heat of reaction from a molecular point of view. As we said, formation of bonds is an exothermic process because you're going from far apart to close together. And bond breaking is an endothermic process because you had to put energy in to pull them apart from each other where they want to be. In a chemical reaction, let's say that the following happens. let's say that the formation of products, which is bond formation, which is exothermic, does not release sufficient energy to pay for the breaking of bonds in reactants, the reaction therefore has a deficit. In other words, that reaction needs more energy than it's able to generate. And so it has to get that energy from somewhere. Where does it get it from? It gets it from the surroundings. And what happens is the surroundings lose thermal energy, and therefore their temperature drops. And that is an endothermic reaction. It's taking energy from the surroundings. If, on the other hand, the formation of products, which is exothermic, releases like a lot more energy than what was required for the breaking of bonds, you now have a surplus of energy. That energy has to go somewhere. Well, it's going to be transferred to the surroundings. The surroundings are going to increase their thermal energy, which means their temperature is going to increase, and that is an exothermic reaction. It's kind of like business, right? You basically, you're going to sell something. You have to invest in materials and work and what have you, and then you sell your product for a certain price. And then, of course, what you do is you count, how much did I get? How much income did I get? How much did I spend on making the product? And so you subtract those two and ask, am I in a deficit or am I in a surplus? Am I making money here or am I losing money with this business? All right. It's very similar to that, because in many ways, the exchanges of energy are like transactions. It's like a business transaction. There always has to be a total net that is the same. All right. So that's pretty much the way this works. Now, let me do this. I want to finish up today's talk with a philosophy appetizer. And this is Dr. Diez's first law. All right. So let me take you back here. Let me talk to you for a moment here. All right. Okay. So I moved to California. I mean, I was born here, but I didn't grow up here. But I moved back to California about 20 years ago. And at the time, there was one of those gas crises. The price of gasoline was going up and stuff. And it was kind of the dawn of the all the technology and all the digital era still. And there were no apps back then. There were no smartphones. There were computers, and there was Windows, and there was Apple, and there were websites. And so a friend of mine found this website where he could punch in his zip code and he could find out where was the cheapest gas around. So I said, well, let's try it out. So we put in our address and found out that the cheapest gas available in the area was about 10 or 12 miles north of where we were. That was the cheapest gas. So I asked him, you realize that to save 20 cents a gallon in gas, you're going to have to spend it driving up there to get it. So is it not a wash? Anyway, we had moved, and then there was this family that we knew from before, and they wanted to help us out by bringing us dinner. My friend, she likes to, get, deals. And so she had this coupon for pizza where she could basically get, 2 pizzas for the price of 1. And she figured, well, between the 2 families, 2 pizzas should do it. It doesn't work when I have 5 kids. A pizza barely makes it. But anyway, I appreciate the effort, right? So she said, okay, I'm going to get you pizza. Well, it turns out that to get the 2-for-1 deal, she had to actually pick it up. It was not delivery. And she had to drive to the next city over. We lived in Irvine. She had to drive to Lake Forest to get the darn pizza. So between time and gasoline spent at that time of that season, it's probably pretty much a wash. And then the other experience I had this other friend who was a freelance photographer. She did weddings, birthday parties, stuff like that. And she was on the side. It was like a freelance work. And I asked her, how much do you make? And she said, this much. I said, that's pretty cool per hour. That's pretty good. Now, she was also one of these coupon freaks. Now, nowadays, of course, we use digital coupons for most things anyway, but back in the day, you took the Sunday paper and there was a fat, thick section of it was all coupons and sales. So she would spend like easily, 3 hours on Sunday afternoons just clipping coupons left and right. And she told me, man, this week I saved like $25 in my groceries by using these coupons. And I asked her, well, let me ask you this. What would have happened if instead of spending 3 hours clipping coupons, you would have gotten a gig doing photography for 3 hours? How much would you have made? The calculation. And it was, of course, a lot more than the $25 she saved. And I said, would it not be better to, invest your time in your craft and make more money and not have to worry about, saving on coupons, spending 3 hours clipping coupons? Anyway, they're good friends. I mean, there's nothing, nothing personal there. I was just thinking, right? And it occurs to me, this is the universe. Every process that happens in the universe has a cost. That cost is energy. Because energy has to be conserved, any process is going to require energy spent somewhere and taken from somewhere else and releasing energy somewhere else. All over the place, every single process in the universe has an energy cost. And so I give to you my version of the first law. You heard the law of thermodynamics. Energy is conserved in any process. No energy is created. No energy is destroyed. So here's what I'm going to tell you guys, and I want you to remember this for your life, okay? There is nothing free in life. You pay now or you pay later, but you always pay. That's Dr. DA's first law. Please remember it always. People ask me sometimes, they think I'm kind of naive, that I don't look at, how do you know your students are not cheating and stuff? I tell them, I trust them. I trust my students. And even if somebody cheats, even if somebody tries to get an unfair advantage in any process in life, it doesn't have to be school only, it can be anywhere else. You know what? Someday, somehow, at some point in time, in some place, the invoice comes in and you're going to have to pay. So it may be not my role to charge, but definitely that is something for us to think about, okay? So hope you enjoyed that. I love sharing that with my students. And let me repeat what I've always said. I am very proud of you. You guys are awesome. Thank you for putting up with this set of circumstances and giving your best. And I trust in you. I know you guys can do it. I'm here to help you succeed and finish out the course, okay? So we're going to cut our recording here.